Hello everyone, as Michael mentioned, I'm Alex. I'm founder and CEO of Pauwels Labs, which spun off Bitmantle, which is sort of the product that I like to talk about now. My info is up here if you want to contact me for anything at all related to this or even not related to this afterwards. Please feel free to. I'd be happy to talk to you. So this presentation is basically an overview of how to burn down a perfectly good savings account by giving AWS your personal credit card number. So how it started was about a year and a half ago. I was coming out of building my second internal developer platform at a fintech company, and out of those two experiences, I noticed a lot of overlap and similarities in what companies want as the sort of the final end goal of having these platforms. And I figured there was a way to assemble a base that you could deploy that gets you 90% of the way there without spending like the 6 to 12 months it takes to build this, basically the basic requirements bespoke. And on top of that, I'm a huge proponent of open source technologies. This laptop is actually an open source hardware laptop. It runs all open source software. And I believe that we're spending way too much money and we're giving way too much trust to as a service products. And I wanted to try and replace every single thing typically solved with as a service product with open source products. So this is basically the story of how I built that, how you can think generically and model platforms, DevSecOps platforms yourself, the advantages of building it this way, and sort of cost optimizations you can apply that I'll talk a bit about at the end. And at the end, all these things I'm talking about, there will be links to actual implementations that are available open source on GitHub for you to peruse and complement this presentation with. So at the base of this is what I call the computer model of software infrastructure. And what I'm trying to get at here is that you as an infrastructure engineer, when you're building these platforms, what you're actually building is a large distributed computer. That its goal is to take code from a developer's laptop and serve it to a client. And just like a computer, you have various levels of abstraction that build on top of each other to reach a space that's leverageable abstractly without having to deal with the low-level components. So if we start this analogy, let's talk about computers, and at the lowest level you have hardware. This is actually a picture of the hardware stack of the first computer I ever built many years ago. And that is sort of the base components that build up the computer. And then on there, it bootstraps the BIOS, which is the next level of abstraction. It takes these individual components, right, and assembles them into a cohesive whole, like one computer. The BIOS is going to bootstrap your kernel space, right, which is where the abstraction really starts to get interesting because the kernel is going to expose an interface that allows you to deal with things like a processor or an audio card. And it then is going to use drivers to translate that abstract interface into real hardware calls. And then finally, at the highest level, we have user space. We have the application layer. This is where any code can run without having to worry at all about what is building up the computer. And so if we look at this is sort of the 4 different layers of your physical computer. And each of these things has a one-to-one correlation to your DevSecOps platform. So at the lowest level, you have your individual cloud services, right? You've got your DNS, you've got your compute. And then from there, you've got your Terraform, which is your BIOS. It's going to go ahead and assemble each of those individual components into a cohesive whole that are all talking to each other. And that Terraform is going to bootstrap Kubernetes. And Kubernetes is going to be your kernel layer, right? It's going to let you deal with things at an abstract level like a development, a load balancer. And it's going to have controllers in it that are going to translate that abstract concept into a real thing in the cloud. And your applications are going to run inside of that kernel or along it. And by the way, when people are going to be bringing up to you buzzwords like cloud agnostic or we want to be multi-cloud, what they're really talking about without realizing it often is their top 2 layers of this stack. What they really want is they want you to build a Terraform module for Azure, a Terraform module for Google Cloud that sort of builds up this base level of hardware, bootstraps Kubernetes into the cloud, and then allows you to have a generic application layer that can sort of be distributed to any of these different clouds. So let's keep sort of digging into this analogy a little bit. There's some base hardware components that you're going to need for any computer. If I'm wrong here, feel free to call me out, but I'm pretty sure if you don't have one of these, you're not going to have a very useful computer. You have a processor, a graphics card, some sort of storage, some sort of RAM. And I guess you don't really need a network layer, but it's quite useful. And you're going to pick an implementation for each of these things. That picture of hardware that I had shown you, any of these remember these model numbers? We got a first generation i7, a first generation GTX, right? You're going to pick implementations for each of these things. And for your cloud, for your platform, there's also a base layer of things that everyone's going to need. Sure, this is not, you're using some queue, maybe you're using some AI system, but I challenge any software company to build any sort of useful software without these base components. You're going to need somewhere to run your code. You're going to need DNS that routes networking requests to that code. You're going to need some sort of database, some sort of object storage, some sort of place to put your encryption keys that's going to secure all these things. And you got to pick an implementation for each of these things. So in my case, I picked AWS to implement these things. And so here we go. We're going to have EC2 for compute. We're going to have Route 53 for DNS, et cetera, et cetera, et cetera. And once you've picked those things, you can move on to your BIOS, right, your Terraform. And people like to overcomplicate Terraform. They like to make these really abstract modules that are like an env, and have a bajillion things that are all in that module. Don't do that. I always say think of infrastructure by composition, not infrastructure by inheritance. One Terraform module should be one piece of hardware, right? It should be one database cluster. It should be one Kubernetes cluster. Use workspaces to replicate that piece of hardware across different domains, whether that's a different environment or a different team. And that's sort of exactly what I've done here, and allows you to compose a complex piece from simple modules. There's a lot to talk about here as well about multi-account architecture, about how you should do RBAC. I'm not going to get into detail here on this presentation because we could talk about that for the next 2 hours, and I'd be perfectly happy over here, and I don't think you would. But if you want to talk about how I would structure that in a way that makes it really easy to build these modules, I'm happy to do that later. So now your Terraform has assembled your base cloud services hardware, and it's bootstrapped your kernel, which is Kubernetes. And let's look at how the kernel compares to Kubernetes. Your kernel exposes, as I said, these abstract concepts, and your application is going to be able to make kernel space requests that are like, I want to show some video. I want to play some audio, right? And your kernel, using a driver, is going to convert that to a specific hardware call. Kubernetes is the exact same thing. Your application is going to deploy a Kubernetes resource like a load balancer, and the AWS load balancer controller will convert that into a network load balancer. Your external DNS controller will convert that ingress into an actual Route 53 entry. And that finally gets us to the application layer, which I think is the most interesting, what we're going to focus the rest of this presentation on. But your application, right, is your developers now have a code base and they're deploying it, and that's the application. But all your applications, if they just sit alone, they're going to need a set of services that supplement them. And I divide these set of services on these 5 fundamental pillars of what you're going to need in your DevSecOps platform. All right, this is going to be your CI/CD. The computer analogy here would be your package manager, APT, brew. God forbid you're on Windows, chocolatey. Then you're going to need some sort of identity management, all right, to handle your MFA, your SSO. Computer equivalent would be obviously your user login. You're going to need a place to put all your config secrets, right, like your database credentials, and provide them to your running applications. This would be like a read-only file system. And then you need observability. This is your task manager, right? It allows you to see how much resources you're consuming, where your network requests are going, and alert on those things. Call that engineer in the middle of the night and tell them to know that something's going wrong. And all of this is tied together using a service mesh, which is your networking component. All right, it's going to allow service-to-service communication. It's going to enable authentication and authorization to those things, and it's going to allow you to either allow requests to happen or not allow requests to happen at an infrastructure level on top of your app level security. And just like we picked specific implementations for our cloud services hardware, we got to pick specific implementations for each of these components. And in my case, these are the implementations I picked. I like to consider this sort of a best-in-class of open source software that you can use to fulfill each of these needs. For continuous integration, we're going to use Tekton, which basically allows us to run our pipelines as containers in our Kubernetes cluster. For continuous delivery, we're going to pick Flux, which allows us to define what the inside of our cluster, all the things that are deployed to it in a Git repository, and then it's going to listen to the changes of that repository to update the state of our cluster. Identity management, we're going to pick Keycloak. I think Keycloak in features and security easily rivals Okta, Auth0, any other service out there. For config security manager, this one's going to be a little controversial with the recent open source issues, and I am actually looking for some alternatives to Vault. It also doesn't have the best UI, but it certainly gets the jobs done. It has high security, and it will interface very easily with your applications and Kubernetes. For observability, I cannot speak highly enough of the Grafana stack, we were just seeing a presentation about observability. The nice thing about Grafana Stack, Mimir handles metrics, low-key logs, and tempo traces, is that they really pioneered the use of S3 object storage to store and index all your telemetry. So you don't actually have to deploy Elasticsearch or some complex database that has to run somewhere. Everything gets shipped to S3. You can define tiers, so old data gets in a cheaper tier. You can back it up automatically. It's super convenient. And then for a service mesh, we're going to pick Istio, which is really nice because it's actually going to deploy a proxy next to each application running in your cluster. And so you're going to be able to, right next to your application, define very strong authentication authorization rules on who and what can access it. So I like to talk about bootstrapping at this point. So what order, how do I set this up? So we're talking about Terraform bootstraps Kubernetes. And the last job that Terraform is going to fulfill is bootstrapping Flux, our continuous delivery system, into Kubernetes. And from there, Flux is actually going to take over. It's going to read our GitOps repo, and it's going to install all the applications we've said need to be in this particular cluster using the resources defined in that repo. And what does that look like exactly? So this is my GitOps infra repo, right? And there's two folders in particular I'd like you to pay attention to here, which is the infrastructure folder and the clusters folder. The infrastructure folder basically has a list of directories, each of which is an application that could be deployed to a cluster. And that application is defined as a set of YAML files, a set of Kubernetes resources that get deployed. And this is basically the list, right? Just like an APT repository of what could be running in a cluster. And then if we look at our clusters directory, it's basically one directory per cluster. And if we look at a specific one, it's a set of YAML files called customizations. Each one of these basically points to a directory in that infrastructure directory that I mentioned earlier. And it's going to say, install this in our cluster. And it's going to allow you to templatize some parameters. So for example, if you're installing Vault in a cluster, that Vault is going to have to listen on a particular domain name in order for you to access its dashboard. And that's going to depend on what cluster, right, you're deploying that to. So those application definitions allow templating and input parameters. So here I'm going to say that, for example, this cluster Vault's going to listen on bitmantle.com. And it allows you to sort of template it and reuse the same app packages. And now if we look at the actual cluster, I don't know how many of you are familiar with Kubernetes, or this is just an command line-based interface, curses-based interface to Kubernetes. I'm looking at our Flux namespace, and it's listing all the applications that are installed in that cluster, the health of those applications, and the revision of the repository when that application was installed. It gives you a really nice high-level overview of what's going on right here. So like I said, right, we bootstrapped Kubernetes, we bootstrapped Flux in Kubernetes, and now it's taking care of installing all the things that are bolded here in our cluster. And that's going to give us a nice solid set of tools, of features on which the applications we're going to deploy are going to sit on. And now we're going to talk about is the order to install these and the advantages we have by having all these tools available and connected together. So the application order is quite simple. It's just depending on who depends on who. You're going to want to install things in this particular order. First comes first. First is service mesh because it has no dependencies and everything needs a network, just about. Then you're going to install your config management. You're going to install your identity management, which means you're not going to be able to provide SSO to things like your config management dashboard. You're going to install your observability system, which needs obviously network access and once again SSO. And then you're going to install your CI system, which is Tecton, because that's going to depend on your config management to get things like SSH keys or authentication to GitHub. And it's going to depend on identity management to provide SSO to the dashboard of it. This is a list of additional quote-unquote drivers or controllers that I like to install that are going to take care of core automations for you. Cert Manager is going to make sure you never have to worry about a TLS certificate issuance for the rest of your life. The cluster autoscaler is going to see how much CPU and memory is being used in your cluster and either get rid of certain nodes or order new nodes. External DNS is going to write your Route 53 entries for you, so you never have to worry about that. And then external secrets is going to be the interface between Vault and Kubernetes. It's going to pull config from Vault, put it in Kubernetes, and allow your applications to read it. Now, why do things this way? I was trying to come up with a list of why this is the best way of doing it, and it all boiled down to the same thing every time, so I decided to summarize it with perhaps an either embarrassing or more engaging haiku. So our haiku is going to be that all things have a place. Like an organized workshop, one thing has one place. And each of these lines means a particular thing. So the first line, all things have a place, implies extensibility. It means that if I want to add a new component to my platform, there's a clear path for how I'm going to add that in. If I want to add a new piece of hardware, a new cloud service, I know I need to go to Terraform, and I need to add it in there. And I know that to interface it with my other apps, I'm going to add the credentials to it, perhaps, to my Vault. And I'm going to add an interface to it in my GitOps repo. Like an organized workshop, what I'm trying to get at here is that your platform is a set of tools, right? Simple tools that work together to provide complex functionality to your applications. And then finally, one thing has one place is quite different from all things have a place. One thing has a place doesn't imply extensibility, it implies modifiability. It means that when I want to change like a config, a database credential, there's exactly one place that has that thing, and I know to go to that one place to do it. And what all this comes together into, and what I'm really trying to get at here, is that I'm trying to make a platform that is intuitive. We all like docs. Docs are important. We need documentation. But as a developer, when I'm approaching my infrastructure, when I'm approaching sort of a platform that's so much better for me, I want to just have an immediate idea of where I need to go to access something. Whether it's config, whether it's my dashboards, there should be one place for each particular thing. And I don't know if you guys are fans of Alton Brown, right? Good Eats. But he doesn't like unitaskers. He likes multitaskers. So leverage the tools that we've deployed as much as possible to do all the different things. You don't have to have a million as-a-service products, each solving one particular problem, right? Combining identity management and a good service mesh provides you a lot of zero trust functionality, which we'll talk about. Rewritten in perhaps a platform engineer perspective, we could say that a metric for a good platform would be, please, for the love of all things that are and will be, stop asking me that. And what I mean by that is that when you come in as an infrastructure engineer to a company that doesn't, they haven't quite transformed, they're still very manual, you're asked to do so many simple things over and over again. How do I deploy a new service? How do I put out a new S3 bucket, get the credentials, and hook it up to my application? Why does that take a week? If you have a good platform, there's a way for a developer to do all these things himself, and a good metric for if you've done a good job is if you're not receiving these questions anymore. So let's break this down to the advantage we get by having all these tools that we've picked, we've implemented, we've deployed them. What does it look like when I want to add a new service, a new code base to my infrastructure? And we're going to go back to Terraform here. Here the analogy breaks down a little bit because I know Terraform is supposed to deal with BIOS and hardware, but we're going to go back to Terraform to create our new services. And we're going to have a services module, and in that services module I'm going to draw your attention to a submodule called service, and the tf-vars file, which is the input to our module. And the tf-vars file basically just has a list of the services in our infrastructure. And we can see that list here has a name. In this case, I was making a Slack bot. Not very creative name, I know. We got the couple parameters like the repo visibility, the domain it's listening on, the envs it's deployed to. And very crucially, we have this thing called template name. And we're going to go through what a template is in a little bit. And then we have the service cell module, and this is going to have all the things that your infrastructure needs to be set up to accept this new service. So we know that a new service needs a place in the registry to store its containers. We know that it needs to be set up in the GitOps repo so Flux knows to install it to the cluster. We know that it needs a GitHub repository. We know that it needs a place in Vault to store its config. Go back to our S3 example. If we wanted our services to have S3 buckets dedicated to them, we could add an s3.tf in here and a value that says, create an S3 bucket for this. And it would go right here and it would hook up the service automatically to it. And I mentioned template name. What is template name? What is a template? And a template is a template GitHub repository or Git repository that provides an entry point for your developers to start writing code immediately without worrying about the infrastructure setup that goes into integrating it into your platform. So in this case, you're going to have one for each of the languages you want your developers to develop in, each language framework you want to use. In this case, I have a template for a Node.js Express app, right, a simple web server. And that template is going to have in its source, right, an entry point for developers to start writing immediately code. It's going to expose a way for them to output custom metrics, custom traces. It's going to have a logging library already set up for it that has structured logging that looks like all the other logs that your organization outputs. And it's also going to be set up to comply to the interface that is exposed by your continuous integration engine. So let me bring your attention to the deploy folder and Dockerfile and Dockerfile.test. I don't want to make a pipeline for every single app. That's a waste of my time. I can just tell a pipeline, hey, when you get a new service, build the Dockerfile, release it, push it, and build the Dockerfile.test, run it, and the code coverage is going to be outputted from it, and put that to our code coverage display tool. That allows me to have a pipeline that's generic to any project in any language without having to worry about the details of what language that project is in. And then the deploy folder is just going to be some custom YAML that needs to be deployed inside Kubernetes to make this app work. So what do we get once we've sort of run our Terraform module, we've added our new service, it's created this code base based on this template. What works right away for one is our CI pipeline. All right, so it's going to start building it, it's going to version it, it's going to push, it's going to test the image, it's going to get the code coverage for it, it's going to release the image in our container registry, and it's going to go ahead and release that image into our Kubernetes cluster. And that includes for PRs. So our pull requests will immediately have chat ops enabled. Our bot, Captain Haddock here, if we have any Tintin fans in the audience, you know what I'm talking about. Thank you. One guy. Whew. He's going to go ahead and test and build our app. He's going to provide us feedback and a comment as to what the code coverage is. And it's also going to give a place for other people on the team to approve our change. And once all the pipelines have run, once someone has approved the change, it'll go ahead and automatically merge this code into my main branch. In terms of CD, we'll immediately be able to see what apps and what services without any of this fancy schmancy Spotify Backstage service catalog stuff, what is deployed where, and in what version that is in that environment. In terms of config, we'll immediately have a place to put the configuration for our app, right? That includes config files and environment variables. It will be able to have a base level of config that's shared across all environments, along with environment-specific overrides. And that template repository that I talked about is going to know, it's going to have some amount of knowledge about this. It'll have a config library built into it that knows how to read the config files provided to it and in which order. So let's move into the security part of DevSecOps. And there's a lot of components to this, but I'm going to focus on this one because it really highlights how once you have these tools working together, you can get very complex behavior out of it in a very simple manner. So that template repository that I showed you that we've just deployed provides this simple Hello World index page. And we see that there's a login button on it. And it's very curious, like how do we already have a login button available? What happens when we click it? And when we click it, we're immediately taken to an SSO page powered by Keycloak that allows us to provide a username and password. It actually provides us MFA as well right away. And when we click on that, it takes us to this secure page, and it already knows our name. So how were we able to have, how complex was it to get this? Well, the implementation of this is 19 lines of JavaScript, none of which actually call any sort of external library or any sort of external auth code. If we look at line 76, you see that all it does is it reads a header called X-forwarded ID token. It checks to see if that header exists. It's going to decode it, and it's going to pull the name out of it. And how do we know to trust this header? Who even provided this header? Well, these infrastructure tools that we've set up, this service mesh with our identity provider, is going to do that for us, actually. Basically, we're able to say, because we're using Istio, that this path needs to have a JWT attached to each request to it. And that JWT needs to be signed by a particular identity provider. All right? And maybe that JWT needs to have certain claims. It needs to have certain roles defined on it. It allows us to define authentication and authorization at the network layer rather than exclusively at the app layer, which allows us to have our security team to independently ensure without looking at code that things are authorized, that certain paths are properly authenticated. And it also means that developers don't have to re-implement SSO all the time, which is one of the most annoying things you could possibly do, and is also quite sensitive. Like you could get it wrong very easily and create a security problem in your company. So basically, all the developer has to do is read this token, and optionally, if you want to have another layer of security, you could certainly verify that it's signed by the right IDP. but your network layer has already done that authentication authorization for you right alongside the app before the request is forwarded to the app code. And this directly ties into any sort of zero trust architecture you want to build. Since Istio is handling everything and it's got a proxy deployed right alongside your app, everything internally is secured via mutual TLS and verified at every single request. You've got this dual auth and auth Z layer that I was talking about, and it allows you to unify all of your auth out of a single system with roles attached to JWTs, right? One human means one user, and that user can have whatever roles we want attached to it. Now we get to my favorite part of the presentation because it's just a lot more visual, which is the ops part. Now that we have all these tools running together in one place, we can have some really crazy cool visualizations of what things are going on inside of our infrastructure. So for example, this is my infrastructure cluster, and this is a visualization of how every single service in that cluster is talking to each other, whether the requests between them are working or failing, and what the volume of those requests are between them. So from a very high level right now, it doesn't make any sense, but what I see is red. You know, that's red in the middle. I should look at what's going on over here. And then if we zoom in a little bit, I like to give as an example the interaction between my external secrets driver, that I was talking about earlier, and my Vault service. We can see very closely that external secrets service is talking to Vault. We can see via the little dots that are normally moving in a particular direction what the volume of that service is between each component. We can see that at Istio Gateway at the top here, we can see external requests coming from my other environment clusters coming in to talk to Vault, and myself coming in to look at Vault's dashboard. And crucially, at the bottom, there's a node called pass-through cluster. And what is pass-through cluster? Pass-through cluster is sort of Istio's black hole that says, it's leaving the mesh. This is going to some IP I don't recognize and I don't know. And that's very curious because I don't expect Vault to do that. And allows me to immediately see that there's a problem here, and I need to zoom in and see what is it doing. And I actually discovered, I believe, if I remember correctly, that Vault is actually calling home here. And there's nothing in HashiCorp's documentation saying that Vault will be calling home at any point to provide any sort of usage metrics or license request, even though I'm not even running enterprise. And with Istio, I could say, well, actually, I want you to block anything going to pass-through cluster. And anything going outside needs to be explicitly whitelisted. And if I flip that switch, pass-through cluster is going to turn into hashicorp.com. And I can see exactly where my external requests are going. Now, of course, we can keep going, not just to network observability, but service observability. We've got our logs and our metrics all under one roof. We can define any arbitrary dashboard in Grafana to visualize these things. This hit counter at the top right is actually a custom metric that just reads the number of times the /hit path is hit. It also includes network metrics that you get right out of the box. See how much network is going in, and you can define alerts on any of these things to call someone if something's going wrong. And this extends not just to an individual service, but your infrastructure as a whole. Right? I can see exactly how much CPU and memory is being used across any namespace, across any application in my infrastructure. I can see the networking that's being used, and I can see, well, why is this one more than the others? Maybe I should look into that. Maybe I should alert on that. So that's sort of the features you have when you follow this model, this computer model of how to build a platform, and you make sure you use multi-use tools and you assemble them together into a cohesive whole. And now let's talk a little bit about what this is going to cost. So your largest cloud expenses by far are going to be compute, right? That makes sense. And cross-availability zone data transfer. This is every gigabyte that moves, for example, from EU West 1A to EU West 1B. If you wanted to use as a service, you didn't want to use all the open source products I made, your largest as a service expense is going to be observability by far. And everything else is pretty much peanuts in comparison. I'll show you exactly why. How can you optimize these things? Well, I don't think there's any in new software at least, I'm not talking about legacy, I don't think there's any excuse not to support spot instances. Every single open source product I mentioned has a high availability mode that allows you to replicate across multiple nodes, which means if any single one of them goes down, I don't see an effect. And your code should be that way as well. I generally say if your code needs a PVC attached to it, it doesn't belong in Kubernetes, PVC being like a hard drive, for those who aren't familiar with that. The moment you attach state to an app in Kubernetes, things become more complicated. Avoid it. State goes where state should go, which is either a database or object storage. Don't write it to the file system. For observability, obviously I highly recommend you self-host observability. And then in terms of cross-AZ data transfer, You can enforce internal communication. So for observability, don't enable multi-zone replication if you don't want 200 gigabytes of data to be copied across 3 different availability zones every time. And that's often acceptable for many organizations. If you absolutely, absolutely need it, Istio actually has topology-aware routing, which will make sure that a request, when originated in a particular availability zone, will reach an endpoint in that same availability zone. It won't randomly pick one. You can combine this with AWS VPC endpoints, AWS private link to make sure that your internal communications never hairpin out to the public internet and back in. So what does this cost? All these features, all these things together, well, it costs about $2,500 to $3,000 a month. And I've seen observability bills that are 10, 20, 30,000 for half the features, and that's just the observability part of their platform. I think for an organization of more than startup scale, this is an incredibly this is a good argument for why self-hosted open source, the total cost of ownership, is not crazy. For the savings you make, you could easily hire an engineer dedicated to making sure all this is running for you all the time. How do I keep from going broke? I created this bash rc alias that I call my save money command. And at night, I just set the auto-scaling groups to 0. This is just a breakdown of things by account and by service. Links to implementation, as I said, all this is open source. You can feel free to derive your own platforms from this right here. And if you have any questions, now's the time. Thank you very much.